All right, so first question is why Unicode? So the thing is that if you look at all the major production languages, they have really good support for Unicode, except for the one that we use, right? So I think this is a defect that should be fixed, right? And I think a big part of fixing that defect is making it easy for like casual everyday users to get into Unicode stuff and be able to write text processing that they can add Unicode support to later, or that just works the first time, because the Unicode processing story in the standard is really good, right? That's really important. Okay, so in particular, a lot of programmers in C++ are Americans. They only speak one language. They don't know anything about all these other languages, right? Unicode gives you some support for getting the right answer for processing in certain ways in certain languages without having to know anything about that language. That's a big win, right? And as an example, like, I don't know if any of you have ever looked at modern Greek, but there's some sort of odd context sensitivity to when you do capitalization in Greek. That's the kind of thing I'm talking about. Like, you don't have to have domain expertise and knowledge. Like, I never knew this until I had to implement it as part of a Unicode library, right? And it would be nice if I could just have used that library and gotten that knowledge for free. All right, so how many people in here know the Unicode terms of art already? All right, yeah, that's what I expected, half-ish, right? So we're gonna go to the very basics of what I'm gonna need to talk about in terms of terminology. All right, so the first thing is a code point. A code point is a character. Note the vigorous quoting. It's not a character in the sense of a char. It's also a highly overloaded term in the Unicode standard. They use character to mean code point here. They use it to mean some other things too. So take that with a grain of salt, but you can think of it as a unit of work in Unicode land, okay? As Unicode is processing text, it does things in terms of code points, okay? Now, code point can be something like the letter A. It can be like, a Korean ideogram. It could be a combining accent mark that goes with the letter A or something like that, right? There's a bunch of different things that could be code points. So it's not a super simple story once you start looking at the code points. A code unit is a unit of work for your machine, okay? Your program deals with code units. A code unit could be UTF-32, which means it's basically a code point, or it could be UTF-8 or UTF-16, okay? And I think everybody kind of gets what those terms are. I'm not gonna go over those. The point is that you can encode a code point as 1 to 4 bytes, that's UTF-8, or 1 to 2 double byte values, which is UTF-16. And then there's this other notion, which we're just gonna call graphemes from now on, because extended grapheme cluster is way too much to say every time. What an extended grapheme cluster is, though, is it's all the stuff that a user, when they see your piece of paper or your screen, final rendering of that text, what they see is one glyph, okay? When they're looking at, this is again from your perspective, reading left to right, if they got the letter A and then an accent, what they see on the page or on the terminal is an A with an accent over it. They don't see the 2 code points, even if you use 2, okay? So, and there's also like combining emojis, which are sometimes very long and sort of complicated. Those appear as one thing in the terminal as well, okay? Okay, so, unfortunately, the industry standard is this thing called ICU. If you don't know anything about it, congratulations, you managed to avoid it so far. But ICU is kind of painful to use. And that's because it's like sort of this weird library that's developed in Java and then ported to C++. So it's not very C++-y. And it is, the good thing about it is it's developed in lockstep with the Unicode standard. So there's actually things you can do with the layout of the actual values of code points and other little databases within the Unicode framework that make it more efficient to implement some of the algorithms. So they're doing all these kinds of neat tricks in lockstep with the development of the ICU library. And so you get some nice benefits from that. Unfortunately, there's no generic programming, right? So you have one string type for ICU. It's a UTF-16 string. You have a type for UTF-8, 16, and 32. Which I did not write here, I think, but I think we've got a different slide. But the idea is if you use a different value type for your code points, or for your code units rather, for UTF-8, let's say, you have to copy data to use the interfaces for ICU. If you stood string, you have to copy data to use their string interfaces, right? So this is not great. They don't have support for saying, oh, I see your string-like thing, and I don't care that it's stood string or my string or Q string. I don't care about that. I'm just gonna work with it. They don't work like that, right? So This is not something we can standardize for that reason, right? We don't have anything in the C++ standard library that works like this, and we're not going to start adding them, right? So here's a concrete example. So you've got this input, which is char16t, it's UTF-16 string, and then you want to write it to this buffer, right? So you say, here's where I want to write the stuff to, here's how much room there is, here's this error code that I have to initialize, here's the input, and I think this means it's null terminated. I'm pretty sure that's why there's no size there. This part's kind of interesting. This says I'm in the English locale, right? That means that because, remember that thing I said before, this is the string lowercasing operation, right? This, if I put GK there, I think is for Greek, or maybe it's GR, I forget which one. But it would do different lowercasing if it saw like the sigma at the end of your Greek word was in the right context for doing the right uppercasing or lowercasing, versus English, it wouldn't touch it. Okay, so there is context sensitivity based on which language you're in. And then of course you put your error code here and you have to check the error code. So one of the messed up things about this is I was just writing this example for this talk. And so I was like, well, I'm gonna look up and see what the error codes that could be here, what they are, right? That documentation is not provided. Like, you look up this function, it's like, there's gonna be errors maybe. And you're like, but which ones? You're like, yeah. So the problem is that I had to look at the source code to find out what the error code is. And there's two things problematic about this error code. One is there's two errors that can be returned. The first one is you made a mistake here. Like you gave me some bad inputs. Why is that an error code? What am I supposed to do at runtime? Like someone wrote the wrong code. Let me fix that now. Like that's crazy. And the other error code is I ran out of memory. I don't know why this thing allocates to begin with, but then you're returning me an error code saying we're out of memory. So this is problematic in a lot of ways. You can see why we can't standardize this. Okay, so hopefully that's motivating enough that we need something better if we're ever gonna have this in part of the standard library. So this is what I would like to standardize instead. We have some string here, and we got this other type, myString. I don't know anything about it in terms of standard library operations. I just know that it's got like begin, end, and it has insert operations. It's string-like enough to work, okay? So with this, I can call toLower, and I've just got like a plain, like standard algorithm looking thing, right? This is the ranges version of things. So I give it a range and I give it an output iterator and I'm done, okay? Easy peasy. Now, this is not actually being proposed. We'll get to that in a minute. Put a pin in that. So again, this is the generic style we're used to from all our algorithms. We want everything to look like this. We want it to use iterators and ranges and be range friendly. So I started all this work with this thing called boost text, which was meant to be like a string replacement, and that somehow got dropped on the floor and now it became a Unicode library. I don't know how I get sucked into writing a Unicode library, but I did. So, and he's applauding, damn you, damn you. So in the process of writing the papers to this, I had to come up with a sort of more concrete rubric than just like, I like this design better than some other design. So these are the things that I have in the papers that are trying to standardize this stuff, like what I was working from, more formally stated, like why I made the design choices I made. So the first one is, as I said at the outset, we want this to be pretty friendly for everyday C++ users that don't know that much about Unicode, right? They should be able to pick these interfaces up, use them, and be able to profitably get their work done without like too much mental anguish. Also, we need to support iterators and ranges. We've already seen that, and I think we saw why, right? Like that kind of interface that I showed for the possible standardization is something that any current C++ user can pick up and like understand what to do with. The old interface requires a lot of like hunting around in documentation. Another thing is that we don't really treat null terminated strings as ranges anywhere, but I'm proposing that we start doing that. And the reason is that null terminated strings are ubiquitous. We get them all the time from C interfaces. Our string literals work like that. We need to have support for those, I believe, as a first order concern. But I think it's easy to do once you realize that this const char star is isomorphic with this, which I hope is not too dim. But this stood ranges subrange, where the first element, the iterator, is that const char star, and then we've got this thing called Null Sentinel here, right? So I could have written this subrange here instead of just the const char star. But what I found was that if I have some kind of adapter that makes that kind of subrange out of it, I basically have to do it everywhere that I've got a const char star or any null terminated string, a w char t star, same thing. So I'd rather the library deduce that for me and say, you know what, this is basically one of these, so I'm just gonna make one of these for you every time I need to, okay? So for all the interfaces, you can feed a range in there, and then you can say as UTF-16, that's a range adapter that makes a lazy view that transcodes from, in this case, UTF-8 to UTF-16. And it's treating that as if it was a range. Yeah?
So how do you distinguish something that is just a regular array?
Yeah, so the question is, how do you distinguish something that's just a regular array? And that's a great question. So this is actually treated as a pointer, right? So we're not detecting regular arrays. Regular arrays.
If you pass in a string literal, that is an array.
That's right. And so array is a range already. So if it's already a range, that's cool. So there's a concept that says if it's a range and it's UTF something as the value type, then we're good. Otherwise, if it's a pointer, do this special dance where you make this subrange out of it.
Okay, so does that mean that string literals?
String literals are already a range.
Right.
Yeah. And it may be problematic for you that you process the null terminator, right?
That's what
I figured that's where you're going, yeah. So it's imperfect and there's no, yeah, go ahead.
I think it's same as string view. If you pass a pointer which is not new to the terminated string view, you just go.
Yeah. So,
but when you construct a string view, that knows that it's a string-like thing. It handles it correctly. It handles it in the way that a naive user would expect.
right. So the comment was,
if you create a span instead, that would grab the null terminator.
yeah. So the comment was string view handles this properly, where you've got the null terminator handled properly, and span does not. And we should do something similar here. Yeah. And this may be a defect.
I'm not necessarily saying what we should do. I'm just saying that it can cause surprises for a naive user.
I think it would cause surprise. I think that's right. So this may be a defect that gets changed in the design, but right now this is what I'm doing. Yeah.
I'm actually doing the same thing in CTRE. And
okay.
Every time it's a pointer, I presume there is a zero terminator.
Right. Right. So the comment was CTRE does the same thing with null terminated strings. Yeah. Did you have a question? Or?
Oh, no.
Okay.
So maybe it's good to deprecate all other uses of CRAs except for string literals.
Deprecate all uses of what?
Of CRAs.
CREs?
C-arrays.
Oh, C arrays. Oh, yeah, yeah. Yeah, that might be nice. Okay, so we can't treat transcoding as a black box. So before you just saw this lazy view, I transcode the whole thing, and that's the only operation that really is supported, right? But sometimes you need to look at, like, is there properly encoded UTF at the end of a sequence or the beginning of a sequence? Where's the break in the middle? Something like this, because let's say you're getting chunks of data over a wire, you're getting chunks of 512 bytes, let's say. Well, UTF-8 could have like a 4-byte sequence as a code point. You don't want to take one of the chunks that happens to end like 2 bytes in and say, okay, that's the end of the sequence. Now let me go process that, because that ending code point is malformed, right? So you might not sometimes need to be able to stitch things together. So there's some utility functions. I'm not going to go over them here, but those are important to have too. Also, it's really common to want to look at the same slice of text in different ways. So I talked about code points, code units, Grapheme clusters before. They form like a hierarchy, right? The Grapheme clusters are made out of code points. The code points are made out of code units. So the idea here is, let's say I have, this is another range adapter, right? This is saying, take that text and give me a Grapheme view of that text. So this Grapheme view, if I say begin and end on it, I get a sequence of graphemes between that begin and end, right? But if I say .base on each one of those begin and end, now I get a sequence of code points. It's exactly the same sequence of code points, but now it's code points instead of graphemes, right? If I say .base on that, then I get the code units. Now there might, if it's UTF-32, there's no code units under the covers, but if it's UTF-8 in this case, there are code units below the code points, and I might want to see those too. So one second. So if I want to slice some grapheme out of this sequence, then I would want to operate on things at the grapheme level, because that's what the end user is going to expect. If I slice in the middle of a grapheme, like some emoji sequence or something, that's going to mess things up. But then ultimately, I want to manipulate some underlying data structure, which is maybe UTF-8. So I want the actual positions within that of the underlying code units. Yeah.
Did you consider trying to have a more descriptive name than base? Because nobody's going to, it's going to be hard to figure out what exactly this iterator means with just seeing base.
At which stage you are? Yeah. Okay. So the question is like, why is base called base and not something like once you put code points here or something? Okay. Yeah. So that's interesting, but I was just following the pattern of the other iterators, like the adapting iterators, all these transcoding iterators are adapting. The way you get the adapted iterator out of it is you say .base. But yeah, there might be room for like an alias of that, like another overload that basically does the same thing. Yeah, it's not very descriptive.
Is it just from STL interfaces or something?
What about STL interfaces? What?
The base method, does it come from there?
No, it comes from like an output iterator.
Well,
Yeah, back insert or whatever. There's a .base, right? You know, any of these.
Reverse iterator has a base.
Okay, reverse iterator. Yeah, right.
And other adapters.
Yeah, that's right. So, but the point is that when you're adapting an iterator, usually you have a .base to get the adapted iterator out of it. Yeah. But that is the case in STL interfaces too, but that's where that comes from. They both come from the same place. Okay, so there are times when you're implementing one of these algorithms, right? In this case, we've been talking about view adapters, but some of the underlying Unicode algorithms, so all the Unicode algorithms operate on code points. That's what I said at the outset, right? But there are cases where you can feed UTF-8 or UTF-16 into them, and you don't actually have to transcode internally into UTF-32 code points because it can just look at the individual values in the UTF-8 or UTF-16 stream and do something more efficient there. An example is normalization, where a lot of your, if you have UTF-8 that you're processing, a lot of your code points are going to be composed of a single code unit. It's because it's ASCII. You're just like, is that less than 128? I'm done. I don't have to do this whole separate step. I don't have to invoke all the logic inside of the transcoding operation, right? So there are some cases where that's more efficient. And so there should be normative wording suggesting that, hey, if there's a way to keep this in UTF-8 or UTF-16 on the input side, just do that, right? And also, the input to any one of these algorithms, in this case, these range adapters, could come from any UTF-N, 8, 16, or 32, right? And we should not have a UTF-8 version, 16 version, 32 version. They should just be one overload, and it should deduce which UTF you're passing to it and do the right thing, okay? And again, that was a situation where I didn't actually have it work like that in the original boost text work. And as I started to standardize it, I realized every example that I wrote, every single time I used one of the Unicode algorithms, I had to write bar as UTF-32 every single time because none of my strings were in UTF-32. They were all in UTF-8 or UTF-16. So if I have to write something everywhere, I should write it nowhere. The library should deduce it. Okay. And we've already seen an example of this, right? I passed in text, which is just a string that's UTF-8 because the value type has a size of 8 bits. It can't be UTF-16 or UTF-32. So it's transcoding inside UTF-32. In this case, for this string, that's a no-op because each code unit is a code point. But in the general case, it would have to do transcoding to make that work, okay? And that happens inside the algorithm itself. That's part of the functionality of the algorithm. You got a question? Does that not make sense? Okay. All right. Another sort of design principle is that UTF-8 is very important. It turns out that UTF-8 is sort of the dominant representation because it's space efficient for almost anything you want to represent. Even the CJK languages, Chinese, Japanese, and Korean, those fit better in a UTF-16 scheme because they fit in one code unit of UTF-16, all the ideograms do, whereas they fit in 3 bytes of UTF-8. Okay, so you've got like a 50% more storage requirements if you go to UTF-8. But then it turns out that like you've got so much white space and punctuation, all this other kind of stuff that you make up a lot of that. And in the case of web, the white space and punctuation actually dominates in HTML, right? So the whole web is UTF-8, even in the Asian languages, right? Even those 3 in particular, but those other Asian languages that are kind of in the same boat. So we should support UTF-8 as a first order thing. That is like kind of what I was saying in the last slide, not requiring someone to do the transcoding manually, like just picking up UTF-8 and saying, I'm going to see this UTF-8 and run with it. Graphemes are also very important. That's going to be the unit of work that most people are going to want to do, they want to use when they're doing text processing. And the reason is what I stated before. You don't want to slice the middle of what is going to be an end user perceivable glyph in the final rendering of that text. Okay, so now the design itself. So the first element of the design is standardizing something that I presented a couple years ago at CppCon, Boost STL interfaces. So this Iterator interface template is part of that. And I wrote it explicitly because I was having to write so many custom iterators for the text stuff that I needed some way of making it easier and making the defect rate lower because, you know, it's very hard to test all this stuff. And so a lot of the testing kind of fell by the wayside. So this is not strictly Unicode stuff, but it's a dependency of all the Unicode stuff. Yeah, Jeff.
So how did the LEWG review go?
The review of it has gone reasonably well. They wanted some changes. In particular, they wanted, I specifically designed it so that it would work with old style algorithms and new ranges style algorithms. And they said no, they wanted me to break the old style algorithm support. So if, in particular, if you make an input iterator using Iterator Interface, it should conform exactly to the concept of Iterator Interface and not provide any extra stuff. So that means that all of a sudden you can't write std copy of that input iterator, comma, some sentinel. It doesn't work. Now you have to write std ranges copy for that to work. Because it no longer meets a lot of the requirements of the std copy algorithm because iterator traits is broken basically, right? That's among other things. Yeah, but it's going pretty well. I mean, I think it's on track and we're gonna talk about it in Varna, so. Yeah.
Would it be accurate to say this is the modern ranges equivalent of the old deprecated std iterator template by the Standard Library?
No, not quite. So that is that was meant to be a base class that was gonna a lot of things hook off of it, but it didn't really make it easier to write an iterator, right? You just derived from it. But I should have said like the question. So the question was what's the relationship with the we have the mic now. I'll stop repeating all the questions. Great. But it is pretty similar to a couple of facilities in the older Boost Iterator library. It combines the iterator adapter and iterator facade ideas into one template. Okay, all right. So the first actual piece of this is a thing called Null Sentinel. This is in namespace std. The other things you're gonna see are in like a Unicode specific namespace. But people said like, this shouldn't be Unicode specific. This is generally useful, right? And so the idea here is it's got this dot base, which seems weird, but the reason it's got the dot base is so that slide before works, where I've got an iterator and sentinel pair, and I could say base, 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 base on either side, and it just works, okay? This is where all the important functionality lives. You give me a pointer to some sequence of stuff. I dereference the pointer I'm at right now. If it's equal to this default t, then I'm done. So this works for const char star, it works for all kinds of stuff. It even works for sequences where you have some like sentinel value that's default constructed that you want to have at the end, right? So yeah. So transcoding is kind of table stakes for everything else, right? You have to be able to convert between or among UTF-8, 16, and 32 and all the combinations, right? It's not terribly interesting, but it has to work right and has to work conveniently for us to do anything else with all the Unicode algorithms. And there's this paper, P2728, which is also moving along. One of the things that I have not done to the paper, and so I haven't done to the slides yet, is we'll talk about this a bit later, but you're going to see a simplified version of things. There's actually been a vote recently to make things slightly more complicated. We'll talk about how. So a transcoding view. So we've seen something like this before. We saw the as UTF-16 transcoding view, but in this case, I've got some wchart star, and I want it to be UTF-8, so I just put this adapter on it, and I'm done. Okay, and there I get code units, right? UTF-8 code units. If I were to say as UTF-32, I would get code points. Yeah.
So how do you know that wchar is UTF-16?
Yeah, I should have said this is considered to be on Windows. I mean, this is soon to be on Windows. Yeah, that's right. So obviously wchart is 32 bits everywhere but Windows and 16 bits on Windows. And that's wonky, but the nice thing is this actually works either way. So like if this was code points because I was on Linux, this would still give me code units and this would still give me code points, right? Because it doesn't care what the input type is. It's like, if you give me UTF-6, 16, 8, 32, I don't care. As soon as you give me that adapter, it's going to transcode to UTF-8. If it was already UTF-8, then it's just a no-op and it doesn't do anything. Okay, it doesn't even wrap it. It just gives you back the thing you started with. That's what the range adapter behavior should be. Okay. Okay. And so this again is another example of a null terminated string being used as a range. And obviously the same thing would work if it wasn't a wchart star, if it was a W string or a std string or what have you. Okay. So views are nice because they're easy to write. They're lazy, so sometimes you can get away with not doing all the work. And they compose nicely with the other std views. Now there is a downside though, which is they have a pretty significant performance overhead versus an eager algorithm that does the same thing. Okay. So if I was to write the transcoding operation from UTF-8 to 32, it would be about 3x faster than std range's copy of that same thing like as UTF-32, right? And that's because I can actually do SIMD operations and get this full 3x faster. If I can't do SIMD, it's going to be about 2x faster. But this is a big deal in performance difference, right? SG16, I was the only dissenting vote on this one. They're like, yeah, we don't care. And the reason they don't care is it's a legit reason. And the reason is that strings are small and we don't care about like optimizing these very small strings. The cases where you see the big wins out of this 2x and 3x kind of number is when you've got really long subsequences. If I did the same thing with like a really small string of a few characters, I probably don't see 2x or 3x. I probably see like, you know, something negligible or something much less. But if I'm you know, transcoding like gigabytes of data or something, I see these big factors. But that's just not a use case we really care about. So, you know, I think we should supply the algorithms, the eager versions as well, because sometimes people are going to want to use them. But if we do that, that'll be in another paper. Okay, so we do all the interesting work of all these views in the iterators. The views themselves are just kind of a bag that has two iterators in it or an iterator sentinel. So you can have, right. This no longer exists. This should say UTF-8 to 32 iterator. Sorry, this is a little factory function that doesn't need to exist anymore because I had not realized how CTAD was applying to this transparently. I didn't have to write any, I didn't have to do any work for CTAD just to work. So this has gone away. Anyway, the point is that you have access to the underlying iterators, but they're not like scoped to the views that they live in. They're like used, I mean, they're available as individual entities that you can name and you can use them. So with each one of them, you construct it from two iterators in a sentinel or three iterators. And the value in the middle is where you are in the sequence. So in this case, we have the beginning and the end and these two iterators. So we're going to iterate from here to here. These are the boundaries, right? We do a normal kind of iteration. And in this case, I've got these two things represent the same sequence of code points, just one's UTF-8, right? So we're just asserting this kind of unit test style that this works, okay? So, yeah, an interesting bit of behavior about this is that when you're transcoding from UTF-N to UTF-M, the Unicode standard says you can deal with errors in a number of ways, right? You can produce this thing called a replacement character. So in the output, you just produce this special character that says there was a mistake or there was an ill-informedness. You can abort the program. You can throw an exception. Those are the three things that they recommend you do for error handling. And the one that they recommend, like above all the others, is that you produce a replacement character. So that's what all these iterators do. That's what all these views do by default. The iterators, unlike the views are not configurable this way, but the iterators, you can provide a template parameter that says, here's the handler for an error. But the default handler just produces a replacement character, but your handler could like log, assert, throw, whatever, right? So that means you can pass these any old junk. You can transcode from dev random and it produces valid UTF on the other side, right? And when I say valid, I mean there's a whole lot of replacement characters in it, but it's valid, right? Okay, so each transcoding iterator, you saw this before, it has 3 iterators or 2 iterators in Sentinel, and that's the underlying representation, right? And these things are all bidirectional, so you have to have the beginning and end of the sequence. So for example, this UTF-8 to 32 iterator, const char star, has 3 const char stars inside of it, okay? And this is kind of an interesting point. This is not about memory safety. It might look like it is, but it's actually about correctness. So consider the case where you have a 4-byte sequence of UTF-8, right? And you come to the end of the sequence. And the way this can happen is the first byte of any UTF-8 sequence tells you how many bytes are in the whole sequence, right? So it'll say, I'm the first byte of a 4-byte sequence, let's say. So if you're inside the increment operation of your transcoding iterator and you're reading UTF-8, you read a byte and you see, aha, this is the first byte of a 4-byte sequence. Then we read the next byte, and then now you're at the end. Okay, so obviously that was a truncated sequence, so I need to produce the replacement character there. If you don't know where the end of the sequence is inside the iterator itself, like having the knowledge of where the end is and the outer in the loop itself outside of the iterator, that doesn't help you. Inside the iterator itself, it needs to know I'm at the end now so that I can produce a replacement character. And the fact that that makes it memory safe is a nice side effect, but it's mostly about correctness because you can never produce the correct sequence of code points out of that, code units out of that, if you don't have that end. And because they're bidirectional, you have the same thing where you have to know where the beginning is in case you're starting to go back past the beginning and you need to produce a replacement character at the beginning, okay? All right, so these are all bidirectional, like I said. For the iterators themselves, it's not that interesting. Most people don't want to iterate backwards through UTF-8, but for the algorithms, it becomes very useful. Okay, so now some of you might have already had this thought, like what happens when you do something stupid? So if I give it some UTF-8 text, again, this has to be UTF-8 because the code, the value type is not big enough for UTF-16 or 32. I say, no, I mean UTF-32. No, wait a minute, I actually mean UTF-16. No, wait a minute, I actually mean what I started with. Okay? So what you get is not this deeply nested mess, right? You get something that looks basically like this. Right? You might get this exact thing. I don't know if I finished the wording for this. I think you get that exact thing, but I haven't written the wording for it yet. And so the way we do that is we do something called unpacking. So let's say you just constructed this type. You didn't, get here by using those range adapters with the vertical bar, but you actually just constructed this type. Okay. This iter-t, if you unpack a value of that type, what you get is a const char star. And the reason you get that is it's the type at the bottom. It's this innermost thing that you're adapting, right? So from any nested, arbitrarily complicated stuff, you can say like, I'm going to look inside here. I know this iterator template, right? Because it's part of the standard library. So the unpacking mechanism already knows how to special case for this template itself. It looks at the two template parameters. In this case, there's one and then the defaulted one. So this is 3 iterators, not 2 iterators in the Sentinel. It says, okay, so I know this is something I can unpack out of here. And then I also have a special case for this one for exactly the same reason as part of the standard library adapting iterators. And I'm going to unpack that one, and I'm going to get the pointer type out of it, okay? And I know that this is UTF-8 because this comes from UTF-8, okay? Steve.
So this seems pretty cool, but I'm not sure when it would actually be used.
Well, where it's used
Faster, I think.
is right there.
Yeah,
So-
so why would someone actually write that in reality other than...
Well, so in a generic context, you might pass this to a thing that does this, and then, I don't know, pass it to a thing that does that. I mean,
But if you're taking something that expects the Unicode text, why don't you just pass the original?
well, that's what I'm saying. So you've got, I'm saying like you would maybe not construct this in one piece, but you would maybe have a function that on one branch, it needs to just use the UTF-32 thing you've got here. And on another branch, it passes to another function that inside of it immediately wants to see UTF-16 for some reason.
There will be difference in behavior.
Sorry, what's the difference in behavior?
There will be difference in behavior because if you like convert it, you will get a multi break, and if you just pass it, you won't get replacement characters.
Where does the emoji bucket come from?
If it's in
If the original,
if it's invalid text,
yeah.
then if you process it through, it will produce a replacement character. If
Oh, right. No,
unwrap
that's,
it completely. It doesn't.
yeah, I see what you're saying. Yeah, so that is true. So this, if it has Mojibake in it, it will stay there. You won't get the replacement characters. Whereas if you did any of these transcoding operations, you get replacement characters. But here's the nice thing. This is something that you're going to pass to some Unicode algorithm, and what they all do is transcode to code points, at least notionally. Now there might be an optimization where they don't.
What? But that. What if you have custom error processing? That changes where the error processing is happening and possibly which handler gets executed.
So this doesn't have custom error processing. That only exists at the iterator level. So if you write the explicit iterators, you can change that error processing, but here you always get a replacement character and that's it.
Okay.
Yeah. So hold on one second. So if you pass any part of this, if you chop this off before any of the bars, you get some range. You pass that range to one of the Unicode algorithms, it immediately does the transcoding, and your emoji bucket gets replaced with replacement characters. If you pass at UTF-32, you're on your own, but no one does that, right? But I mean, everybody has their strings in UTF-8 or UTF-16. No one's passing UTF-32 to a Unicode algorithm unless it comes from another Unicode algorithm, in which case it was sanitized. So there is a hole there, but the hole is only for this use case that people don't do very much in practice. Steve.
Yeah, just I think I worked through it in my head, but I want to say, as UTF-8, you're going from UTF-16 to UTF-8. You're handling surrogate pairs in there, right?
Yeah.
So we don't get WTF.
That's right. Yeah.
But that's also important because that's why you can't write this as like just as a transform.
You can't write which part is not as just as a transform?
You can't just convert the UTF-16 to UTF-8 as a transform operation. Take the 16 bits byte and convert them word by word.
Oh, right.
You
Okay.
might have to take two of them.
Yeah, that's right.
And
Yeah. Okay. Right. So the unpacking gets the bottom type out of whatever adapting things are happening here. And this is done through a CPO called Unpack Iterator and Sentinel. So if you have your own transcoding iterator, you can hook it into this mechanism and make it work. Yeah.
Is that stood ranges concept, or is that a Unicode library concept? The inner T and the unpack iterator, is this in Unicode land, or is this a general ranges?
This is a novelty. This is something that I'm proposing that we do. Yeah. And it has to do with the fact that we're dealing with transcoding iterators, which are adapting. The reason why this is not in Unicode land is Unicode land is de facto ICU, and ICU doesn't need to do any of this stuff. Right. They don't have a generic system. Okay. So now we're out of transcoding. Now we're talking about the actual algorithms. This is the fun bit, right? This is the stuff where you actually get work done. Okay, so first of all, normalization. And so if you don't know exactly what normalization is, let's talk about these two strings and I'll make it clear. So let's say we have an n followed by a combining tilde. That's just a regular tilde just so it's easier to read, but it's representing this code point right here. Okay, that's a combining mark. So this thing will combine with whatever letter it has before it if it's a non-combining letter or non-combining character. And then this is an enye, right, which is just the combination of those two. There's another code point that's just the two of them together already combined. Okay? So this is two code points, this is one code point. Unicode says when the user sees this, when you render this into a terminal or on a piece of paper or what have you, it better look like that. And since they look the same to the end user, when you're processing them in your program, you have to process them as if they're the same. Because to the user, they are the same. We're talking about text. Text is about representing things to humans, real humans. So you have to treat those things as the same because to a real human, they're the same. So obviously we can't treat something of length 1 and length 2 as bit equivalent to each other. That doesn't make sense. Even if they were like two different code points that look the same, we would also not treat them as bit equivalent to each other, even though they look the same. So we have to have a way of putting them into the same format so that we can do bitwise comparisons amongst them, right? And that's normalization. I talked ahead of my slides. Yeah. Okay, so this is what I just said, and that's the paper where you can find more about this.
Is it algorithm or view?
In the paper, it's an algorithm, and it's going to be a view very soon. And because the algorithms are basically the SG16 vote is like, we don't want to see algorithms, we want to see views. And the algorithms, like I said, may be a follow-on paper, but right now it's going to be views. Okay, so there's two major forms of normalization. Taking our same example, like if you've got them separated, the combining stuff that should combine together separate, or if you've got them combined, those are known as decomposed versus composed. So normalization form decomposed is NFD, normalization composed NFC. It turns out that NFC is, again, because of space savings and because like people transmit so much text over wire, that is the dominant form. Everybody basically standardized on this in web, and other people standardize it for a lot of reasons. You might want to have your text in NFD internally if you're doing kind of text manipulation. You want to manipulate the individual combining marks and stuff like that, but people very often just have everything in NFC, I meant to say. And there's these two other forms, NFKD and NFKC, which are these compatibility forms, and they're useful for things like comparing strings to each other and like reducing the differences between them if you're trying to do like searching and stuff. For most users, you can kind of ignore these, but they do have their uses. Okay, so here's an example. Again, this is in the form of a view. This is not what is in that paper that I just mentioned, but this is what's going to be in the paper soon enough. So let's say we put this combining tilde here right after this N to spell senora, and here's the actual result. So remember, this is a Unicode algorithm. It operates on code points. That means even though we have this interface nicety where it'll take UTF-8, it produces code points, right? So you want to compare it against something that's UTF-32. So here's a string literal that's already UTF-32 with the ENYE already in it. So this is the NFC form, this is the NFD form, but this whole expression ends up being NFC because that's what the view adapter is doing. So if I combine them, binary equivalence, that's where the binary equivalence is, right? Okay. So there's a wrinkle with normalization, which is you can take two things that are normalized the same way and you can combine them. You can also take something that's normalized a certain way and you can take something out of it and all of a sudden it's not normalized anymore, the same way it was. So for example, like senor, which is not a real word, this is in NFC. There's no combining marks that are hanging out here that need to be combined. This is also NFC because there's no combining marks that need to be combined with something before it. If there was a character before this, this would not be NFC, but by itself, it's NFC, okay? There's nothing that needs to be collapsed that's not collapsed. If I insert it here, all of a sudden I've made it NFD, right? And if the rest of it had combining marks, it's not NFC or NFD, it's just broken. It's not in any normalization form, okay? Because now I've got this combining mark that's after an N that can combine with and it's not collapsed, so it's not NFD anymore, or NFC anymore. So how do we fix that? Well, it turns out that you can do some fiddly business and make this work for these three algorithms I'm proposing: normalize, insert, and erase, and replace. Okay, and what those do is you've got a section of code before the insertion point. Let's say not code, but a section of code points, right, before the insertion point and then after the insertion point. You insert some text, and it turns out you can look at a limited amount of the stuff before and at the beginning of the the inserted text, and you can just normalize that stuff, and you end up normalizing this end of it. You can do the same thing on the back end and normalize that stuff, and now the whole thing's normalized. You don't have to normalize the whole thing. You can take these small subsections, and there's some ways you can detect how much you need to go back and look at or go forward and look at that's specified in the Unicode standard. Okay, so this is all very fiddly. There's a bunch of cases here. It's hard to implement these, but everyone's going to need them if they want to keep any of their text in normalized form. Okay, so here's an example of use. Let's say I've got this UTF-16 stuff up here. I copy it into this vector. Then I've got this stuff I want to insert, okay? Now the actual function is down here. So this is, I don't know, maybe not the greatest example because I'm replacing the whole thing with something else. But it's a general purpose algorithm, right? So I could have replaced just the first code point or something like that. But anyway, so stir is necessary here because I need to see the whole thing, right? I need to see the whole sequence. And because when I erase some stuff here, there might be some stuff before or after it. And when I do the insert, of course, I need the whole string because whatever I insert, I need to collapse with the stuff before and after the place where I erased. And if I was just doing an insert, it would only have this part. And if I was just doing an erase, it would only have this part. But of course, a replace does both. And what I end up with is this combined D with dot above. So it took this input and actually normalized it as it was doing the insert. And there's a flag you can pass to it that says like, hey, this is actually normalized. Don't do that extra bit of work by normalizing this first. Okay. This is, like I said, a very fiddly thing to write. It took me a long time to write it. This actually came out of the Boost review. Someone was like, why don't you have this general purpose algorithm that does this? And I had it as an implementation detail, the string type. And when I broke it out, I realized there was all kinds of bugs with the original implementation. So it was great to do this as an exercise to just get it correct. And it's generally useful for building string types. That's the kind of stuff we want in our standard library, right? Building blocks. Okay, so, yeah, well, you first, yeah.
Go ahead.
Maybe instead of passing stir, additionally, we could use like a vocabulary type, maybe something like a slice that knows from its source.
So you're saying like maybe we could pass a slice for stir here in the beginning?
No, like combine a stir with the with a start, begin, and end in like
So you're saying like this would be a sub-range or something?
yeah, like
Yeah, there might even be an overload that has these as ranges, but believe me, these are going to end up being ranges. Probably there's going to be an overload for those to be ranges. I would expect that. I would expect SG16 to ask me to do that.
I mean, but subrange knows about its full range.
Yeah, that could be possible. You'd have to have like some custom thing that adapts this. But the thing is that like we already have all the operations we need on it. So there's a concept for this at the top of this. Right, the template head has the concept for this, and it's like string-like, right? And string-like is, you know, it basically just has to have like insert, erase, whatever. It's got to have a few operations. Maybe not insert, maybe not erase. I forget the exact details right now. But the point is that like there's a concept for this, and so this is really useful without any kind of particular adapter for all the string types we care about, all the built-in string types, including all their type defs. It's probably going to work for QString and whatever other crazy string types you have in your ecosystem. So I expect this to work pretty well for most people without introducing a new template, I think. But Jeff, you had a question?
Well, you answered my question why the middle, or the second and third weren't arranged.
Yeah, and it might. No, it's not ambiguous. So it might be fine to have just overloads where those are ranges. That probably works. I think I probably didn't do that the first time around because, again, everything I was doing in the initial work was like sort of pre-ranges stuff, and then the ranges stuff got adapted. It got adapted for the ranges ideas. So that's maybe something that should be fixed. Yeah.
Something just to keep an eye on. So some of the linear algebra work looks like they may be ending up specifying a type where those two wouldn't be iterators, they'd be locations in the range that you're
Right. So this would be like,
well, yeah, wherever you want to do it.
Yeah.
It's like because there needs to be a connection logically between some of these parts.
Well,
You should not say copy over stuff there looking at
yeah,
this
yeah.
string over
Take
here.
this string and some other string and replace these parts of this string. Like you can have a mismatch with the pieces. Yeah. So if you had like,
So I think
and
it's
this
like
might be
index
kind of what
type
you're,
sort of thing.
yeah, this might be kind of what you're talking about. So if you had like a slice function that returned a thing that knew about, like it knew how to take that stir that you give it. So you're passing stir, slice of stir, something like that, right?
Yeah.
And I know they're doing that in the linear algebra stuff, and you know they've got niceties in there, like the two boundaries that you pass in can be negative indexed and stuff, just like Python. And yeah, there's probably some room for that. But ultimately, what that would do was it would generate a range, so
Yeah,
this
it's
function wouldn't
yeah,
change.
It's more like
Exactly.
keeping some of the easy errors out of the interface.
Yeah. And so that would be a nice interface. And if that facility works, not just in linear algebra case, but in the general case, then we could use that here for sure.
Use that.
Yeah.
It's just something to keep in mind, like at the end of 25 when we're all landing all these things into.
We're trying to make sure that they work together. Yeah.
I would call it
Okay.
a rich spanner.
Sorry, what?
I would call it a rich spanner. Like it would be span with
A range spanner?
rich spanner.
Oh, okay. Yeah. I have no idea what they're calling it right now, but yeah.
Every time I look, there's another name for it.
Okay, so I've alluded to this a little bit. So the transcoding that happens in these views, right? So all the algorithmic views and all the transcoding views themselves, they do some transcoding, right? The transcoding views are all transcoding, but the other ones transcode at the boundary, like to get into code points to do the Unicode algorithm. So the question is, how does this work? Well, each view looks at the range before it that it's given, and it determines whether or not it's UTF-8, 16, or 32, or if the code is ill-formed because it's none of those. And there's some things to keep in mind here. So on Windows, you've got WCHAR-T, and that's UTF-16. Of course, the same thing as WCHAR-T is also UTF-32 everywhere else. You've got ICU, which uses char, char-16, and int. I don't know why. For the UTF-8, 16, and 32 code units specifically, respectively. You've also got non-Windows, non-EBCDIC users who basically are using char for UTF-8 everywhere, right? Because it's the standard everywhere except for IBM mainframes and Windows, that I can tell. And then you've got char 8T, 16, and 32T, the char NTs, is what I'll probably call them from now on. And those explicitly claim that they are encoded in those respective encodings. And when you do a string literal with U8 or U32, you get these types. Okay, so we need to support all these, in my opinion. So my way of supporting all those was to say the concept that matches UTF-N, or it says I have some kind of UTF on the front side of my, before the bar in the range adapter scenario. The way I determine that is I look at the value type of that range, and if the value type is an integral type, that's the first requirement, and then it has to be exactly n bytes for UTF-N. Okay. So that fits all those cases. It doesn't work if you've got some exotic system with a 9-bit char. It doesn't work for that.
32-bit chars.
Yeah, 32-bit char, stuff like that. Yeah, it doesn't work for some of those exotic systems. But you can actually specify that the value type has to be exactly n bits, and then not do it in terms of char and char AT and so on. You can just say like, the implementation knows how many bits that value type is. As long as it's integral and it has the right number of bits, I don't really care, right? Whoops. Oh yeah, I didn't say the part at the bottom. Yeah, so SG16 wants this to be same as char NT. So they want to only support char AT, char 16T, char 32T, and that's it. So if you have ranges of those work. String doesn't work, char star doesn't work, wchar T on Windows doesn't work. Those things don't work. Okay. I was, again, the only dissenting vote, just for the record. So with the SG16 way of doing things, you have to put like, no, I mean it, right, in there, and then you get to do your range adapter, right? So in this case, I've got a sequence of char AT, so this is just fine. Here I've got a sequence of char, and so this doesn't work. So all the slides you've seen so far have been lies, because I wasn't doing this, but this is what is going to end up in that paper very soon, right? I am very much against this, and I predict this will not survive contact with LEWG. So I don't think this is going to end up being in the final version, but this is what SG16 wants. This is the status quo right now. Okay.
Maybe we need not an is integral test, but is character trait.
Well, so that doesn't work for int, right? And that doesn't work for ICU. And so I think that's an important migration story. If we want people to get off of ICU and start using the standard version of things, we have to have an interop story for intermediate code. I think that's really important. It also doesn't work for, some people have like uint16t, right? Because they were working on, they're working on a system where they had to have portability, so they didn't want to use wchar-t. It was pre-char16t, and they still have uint16t around or something like that. Yeah.
Could it be a platform-defined concept?
Yeah, so that's interesting. So we could define it differently on different platforms, but I tend to dislike those approaches just for the portability reason. The same reason I don't like wchar-t being different sizes on different platforms, right? But I think ultimately, like, it might be possible to say something like, it works for char NT, it also works for char and wchar-t, and maybe that's it. And if you want to do something else, then you do have to do this, because it's much more likely you've made a mistake. But I think that, like, so if I had a function overload and it took the wrong set of types, and a bunch of those types made the code not make sense, or they would do something but it's not what I meant, then that's a dangerous overload to have in my overload set. This is not that case. I had to explicitly write bar something. Right? I had to say like, that's what I want to write. And then I wrote bar this, right? So.
Isn't this problem also with constexpr? Because it won't be constexpr anymore. The UTF-8 for RLCs.
I don't understand what you're saying. What about constexpr?
You cast char into char AT, and you cannot do that in constexpr.
Right. So what this would do, so there's actually ways of making this work. So this has the high level semantics of a cast, but I don't think it would actually use a cast under the covers. Essentially what you would do is you would say like, if I see that it's been decorated with this, then I know that this can do exactly what it does in my implementation right now, right? So, but there's actually like a different proposal somewhere in the pipeline to make casts among character types in particular work so that you can have char AT and char interoperate with an explicit cast. And I don't know if that would be like a new style cast, or it would be like changing the semantics of static asset seems super dangerous, or I'm not sure what form that would take, but someone's working on that. Do you remember the details of that, Steve?
Yeah, I know. I don't remember who it is.
Okay.
But yeah.
All right. So I wish I had a paper number for you, but someone is thinking like along those lines, but I don't think what we would do here. So
And sorry, why does SG16 hate the nice way?
because they don't like nice things. I think what is going on is they feel that the char, char at doesn't alias. It's better than char for that reason. It comes from like string literals. So if I put U8 in front of a string, I get a char at, not a char. They're basically saying like char at is the future and we should support the future. But I'm like, well, I live right now, and right now I need string to work. So that's a problem for me. But Steve can give more rationale.
On the other side, it's like I'm in a multi-encoding environment. Well, my literals are UTF-8. The data that's held in any string, there has to be something else that tells me what encoding it is. And it's hard to review code that isn't there.
Yeah.
Someone will take that string, treat it as Unicode. The code will look fine.
Yeah.
I see.
But
For instance, like your chars on Windows are very likely to be Windows 1252, right? Because that's like
something, yeah.
Like if you get data from the terminal, that's the default terminal like encoding, right? So that's a problem if you use char, right? But my argument to that is, yeah, of course, but it's the same problem if you use char at, because I can read some stuff from the terminal and store it in a buffer of char at, and it's still Windows 1252. I didn't fit, like char and char at have the same invariance, which is none. They don't maintain anything, right? So to me, this is an academic argument, and what this is saying is like you didn't meet we have philosophical disagreement that makes you write more code, and I don't like that. Yeah.
Well, I would argue that even if char 8 and char 18 don't enforce anything, they still have a different meaning.
What's the different meaning?
Because in terms of if you see someone loading arbitrary bytes into char, that's not necessarily wrong without any validation. You don't know that that's wrong right there. If you see them loading it into char 8 without any validation from an unspecified source, that probably is wrong.
Yeah. I mean, I think that's fair, and that was part of the justification for char at is I could provide overloads to functions, one that takes a char star and one takes a char at star, or some range of those two. And I can say like the first overload is like, I don't actually know the provenance of this. And the second overload is this damn well better be UTF-8, right? So that's a reasonable thing to do. But I think that the problem comes in when I can't print, I don't know if you guys know this, but I can't stream a U8 string, like it doesn't work. Mm-hmm. Like I have to work in U8 strings. I have to work in unprintable text. What am I doing text with? I'm printing it, right?
You can format and print though.
You can format it, right? But you can't stream it, right? But so there's a whole bunch of there's a whole bunch of weird things going on here, right? So I don't want to harp on this too much, but I think this is the wrong decision. I think that we should eventually like all be switching to char at if that makes sense in the future, but right now we can't, and that's my problem.
The other place where all of this is problematic, I/O boundaries. Car 16 comes in over the network in octets.
Yeah.
And those are cars.
Yeah.
So you're going to have zeros between every one of your
Probably have to rebyte or
Still byte.
anything else, right?
To the byte.
stud bytes. Yeah, it's like you can use it for I/O, just don't use it for anything.
Yeah.
No, actually, don't. No, I'm sorry. Stud byte only used for memory, and aliases don't use it for I/O.
All right. So text segmentation.
Zach just
So-
wants to get off that.
Yeah, I want to move on. So text segmentation works like this. So you take all the code points in some chunk of text, you convert every one of those code points to a some kind of property that makes sense for this segmentation operation you're doing, word breaking or whatever, and then you do the algorithm on the properties. Okay, that becomes important in a minute, but for most users, they can kind of ignore that in its implementation detail. So there's breaks for finding grapheme boundaries, word boundaries, line boundaries, sentence boundaries, and there is a paper 2745 which has not appeared in a mailing yet, but it will shortly. So first of all, we've talked about graphemes before. It's the notion of like one user perceivable character in the output of your text. So if I want to see the grapheme view of this, I get this. And what this actually produces, the value of this Grapheme is something called a Grapheme view. And that is, formatable, printable, streamable. So you can directly use that and spit it out to a terminal if you want to. Or you can say, dot base and get the code points and code units out of it as you need. So there's also word breaking. Word breaking is just what you would kind of expect. It produces these boundaries. And so like punctuation and white space are usually their own words. And the nice thing is now we have the composability with the standard adapters. And so in this case, I want to just go backwards. This is why those adapting iterators are bidirectional. And here I just print out this word, and it's the second one, which is right. Yeah.
Does this work for languages that don't use white space to distinguish separate words?
Yeah. So the word breaking algorithm basically doesn't work for CJK at all. Because if you have like a whole bunch of Korean text, there's no word breaks. I mean, so there's no white space or sentence breaks. So you have to do a different algorithm. And so this is one of the many Unicode algorithms that's like, we work for a lot of languages, but we don't support everything. And like I said, there's a whole bunch of them, but the word break is a pretty big one. Does someone else have a question? Did I see a hand go up?
Would that let such a language pass through this pipeline, or will it consider it like an error to use words on such a language?
Yeah, it's not going to be an error, but I think you get one big word.
Yeah.
One big word.
I think you get like, yeah. Show me where the words are, and you get yes, right? That's not what you wanted. So word breaking, yeah, go ahead.
Is it possible to add this as an extension or specialization?
Yeah, okay, so that's a great question. So the idea right now is to standardize this, and then that is a view adapter, right? So we can parameterize a view adapter, right? So later on, we could put parens locale. And you could maybe have a CJK locale, or specifically a Korean locale. And then it could say like, I know an algorithm that works pretty well for breaking up Korean text into words. And so I'm going to do that. Or sentences or what have you for the sentence one, right? But the idea is for now, we're just going to do the vanilla one. That's the vanilla description of the algorithm in the Unicode standard. And then if we want to have like all the niceties that ICU does, that will be in a later version. Yeah. Okay, so word breaking is really application specific. So if you go in your favorite terminal or your favorite word, your text editor rather, you're going to find the word breaks are in different places, right? You move forward or backwards one word at a time. You go to different places. You double click in the middle of a word. You select different stuff. So word breaking, in fact, a lot of the Unicode algorithms are meant to be tailorable. And often that tailoring is for things like I just mentioned a second ago, like the specific locale, right? Or specific languages or whatever. But you will also probably want to do your tailoring on an application level. So for the word breaking algorithm, this is what we do. The first thing is you can take that property mapping function where you take a code point and you map it to a property and you can edit it, right? You can provide your own property mapping function. So here's the default behavior. If I print out of the box, you see where the line breaks are here. I hope that's not too dim, but it produces breaks around all the dashes and around all the words. Okay, but then if I give it a different property function, in this case, the property function defaults to the built-in word property function, but in the special case of a dash, it says the property is actually mid-letter, which is not the normal property for that. Mid-letter just means I could be in the middle of a word. Mid-letter and all the other properties are part of the Unicode standard, so I kept the casing the same as the Unicode standard. So what that prints is out of the box all as one word. Right? Because now the dash is considered to be the middle of the word. Okay.
Could it be
Yeah.
that it depends on multiple letters if there's a word break?
Funny you should ask.
Ah, okay.
So let's say we've got a different scenario in which we want to take these identifiers that we have in some programming language and we want to break up the chunks of the identifiers. So we want to have a break here between camel and case and the breaks around this underscore, right? So right now it prints out this and then that as two different words, okay? Those are considered whole words. But we can give it a function that takes context from before the current character and after the current character. These are the two code points before and after the current character. This is the code point at the current character. And if we return true here, that says force a break right before this character. And false means just do the default algorithm and don't mess with things.
How
Steven.
much context can you ask for?
That much. Two is all. So the reason I picked 2 was because it turns out that to implement the word breaking algorithm, that's all the context you ever need. So I said that's all the user is going to get for customization purposes. Yeah.
Are those graphemes code points or?
Code points. Yeah. So the algorithm always operates on code points. So yeah, those are code points. Yeah.
So what are the previous and next at the beginning and end of the?
They are, I think, 0. Yeah. So the idea is, if you're tailoring on 0, then, whatever. They could maybe be optionals or something. I think that 0 is sufficient for almost everybody, though. Steven.
I just want to elaborate. The algorithms all operate on code points. They know about graphemes and grapheme clusters. They do the right thing.
Yeah.
It's just baked in.
Yeah. So you can see this logic here is like on either side of an underscore, or when you've got a lowercase followed by an uppercase Latin character, then you produce the break. And so now we get a break around snake, around case, camel on case also. Yeah.
It almost feels like, like a fixed size array instead of 5 parameters.
Sure. We could provide like a span, right? You could even say like, give me this much context and I'll give you a span of 7 or 10 or whatever it is, right? Not 10, but an odd number, right? Okay, so yeah, that could be a possibility.
That seems like it would be a cleaner interface for that
Yeah. Okay, so you could also break up sentence boundaries. So there's the sentence example. Give me the third sentence and some text, right? That's pretty straightforward. The line breaking is kind of odd. So line breaking, the default line break is, the default line breaking adapter, right, is break lines at a hard boundary. What that means is I put a new line or a carriage return followed by a new line or one of the other new line characters from Unicode. I put them there. So that's where the break is. So if I print this out, I'm going to get this stuff broken up by new line sequences only. Okay, so this is the third line. If I reach the third line out of this this text as far as where the hard line breaks are concerned, because they're actual line break sequences. Now, there's a much more common case for line breaking, which is I have a certain amount of space and I want to put text on that line until I run out of space and I want to go to a new line. Jeff.
I want you to go back. So
This one?
yeah. So what do you do at the beginning of the sequence?
Well, someone already asked that. Thanks for paying attention.
I thought I was.
So the beginning of the sequence is probably going to just be 2 zeros, right? And at the end is going to be 2 zeros for the. Sorry?
It won't work with span.
Yeah, so a span wouldn't work in that case. That's true. Yeah.
Okay, that's right. But what happens if you have a span and you require a span of 10 and you're at the beginning?
Yeah, so I mean,
fill up your span?
what you might be able to do is provide a span and an index, and the index is cur, right? Then you could lop off the span, like cur would be 0 for the beginning and cur would be n-1 at the end, something like this, right?
I guess I don't understand though how if pre is actually 0. You can't give it 0, can you?
Yeah, I mean, so that's what I did for my example, because like for interesting cases, like you don't deal with 0 boundaries really in most text, right? I mean, embedded zeros in the middle of text defining where your word breaks go, that's not a thing, right? I mean, that's not a use case anyone cares about.
Right. I've only used embedded zeros to find ways around blacklists.
Right, yeah. Okay, so all right, well, we need to move on though. We're almost out of time. So let me get to this part here. Yeah, so we want to know, given a certain amount of space, how many things fit in that space. So in this case, I've got 60. In this case, it's columns, but these units can be whatever you want. It doesn't matter to the algorithm. And then somehow you have a way of estimating the width of a range of code points. So this is iterators to code points. There is an estimated width function that exists in your C++ standard right now as of 20. It's not exposed as a thing you can call, but it has to exist because format needs to do the same operation. So this is using the same logic that exists in std format. So given some range of code points, this is how much space they take up, and I'm going to accumulate that space until I run out of space in the 60 columns, and then I'm going to do a new line, right? And so that's like a word breaking thing where you don't have like a word chopped in the middle. It's going to break it up based on words. There is a peculiarity, which is if you found a hard line break, so this line thing is not just a range, but it's also like has the information of whether it represents a hard line break or not. If it does not, you need to put your own new line. If it does represent a hard line break, there's already a new line at the end of it, so you don't have to put one. And this is a forward range. It's one of the few ranges not bidirectional because you have to like accumulate all the results to do this current line you're on. Okay, so there's also a case mapping that should be adapters, not functions. Both of these things that I pointed out are bugs in the slides were fixed in the other version, but then I did not pull the right stuff. Okay, so string to upper does just what you would think it does. It produces code points that are the uppercase version of that given string. Again, this is the vanilla version of the algorithm. So at the beginning, I was talking about like the special casing of Greek text. We're not doing that here. That would be some future version where you put parens like GK or something. Yeah.
When you would want to change to a different language, have you to put it at every call, or would you have like an environment call that switches the whole environment to?
Yes, you would want to put it at every call. And the reason is that right now we have global locales and everyone hates their lives because of it. Yeah, it's not a good way to do things because that globality is a super problem, right? It's a big problem. Okay, and also that you're seeing these predicates here if something's uppercase or lowercase already. If you wanted the output to stay in UTF-8 because it produces code points, you'd put the adapter after it to say, take those code points and produce UTF-8 from it. And then there's the bidirectional algorithm. This one's super complicated to implement. It was the biggest pain, but it's really fun. So the idea is you've got up to, wait for it, 127 levels of nested right to left within left to right within right to left with the left to right context. 127 of them. That's in the standard. So you have to support like basically arbitrarily nested left to right to left text. Okay, so let's say we have some Arabic here, and that is this string that I put into Google Translate. I don't know, that could be complete garbage, but it produces that. So when you see it in Google Translate, this is what it produces. You can see like hello, comma. So you're reading it right to left. Okay, thanks. And then what? Oh, okay. So in memory order, though, obviously you want the first stuff in the sequence to be first in memory. So we're writing stuff in memory order, and in my terminal, everything is left to right. So in memory order, it looks like hello, comma, whatever, right? And you can see this is very different from the original text that we started with. It's in proper right to left order. But if you take this in memory order, where the hello comes first, and then the comma, when you print it out to your terminal by chunking it up into sequences, it gets printed out this way. So how this works is that what bidirectional subranges does is it produces subranges of text that are right to left or left to right and that fit on a line. So there's another part of the algorithm where just like you can do with the lines, you say, here's my available space and here's how I estimate how much space I'm using up. You can do that here too, and it'll actually do kind of a word breaking, and where you put line breaks is also important in terms of where you put the chunks, because right to left and left to right things get broken in different places based on where the line break is. So you do this one little call and it does all this insane machinery under the covers. And what it produces is this stuff that you can just stream out or print or format out, and it produces this nice result. And so this range is not only a begin and end, but it has the knowledge of whether it's left to right or right to left. And so when you print it or stream it, it feeds the code points out in reverse order of memory layout or forwards in memory layout to produce the right to left or left to right result. Okay? Again, go look at how you do this in ICU, right? This is what we want, I think, to standardize. All right, and I believe that is it. Okay, so if you are curious to see any of the implementation details of any of this stuff, it's in this GitHub repo, tzlaine text. I will warn you that right now it's pretty badly broken because SG16 has been asking me to make a bunch of changes to things that break everything downstream of it. And so I have not caught up with stuff because I'm working on the first paper, which is all about transcoding, and that's the basis operation for everything else that happens. And of course, if you have any objections to any of this stuff or any ideas, please don't hesitate to send me an email or come talk to me later about it, because we're early enough in the process that you can actually have an influence on how this stuff gets standardized. All right. Any other questions? Jeff.
It seems to me there's a bonus here. All of these algorithms now, we would get basically to the place where we could get rid of boost string algorithms?
Get rid of boost string elements.
mean-
I think that's we're close. I think that's true. And
Yeah.
and there's actually, so this came up when we were talking about standardizing string contains and string starts with and ends with. I was like, these should be algorithms. Why are we doing this? Because they don't work with a span. They don't work with a whatever range. That's ridiculous. Why do we have an algorithm hang off a type?
We do have those algorithms.
Yeah. Well,
That's what-
we added them after I had this discussion with LEWG, and there was no plan at the time to add them. But the real issue to me is they should not be attached to string. And the reason is that every time someone wants to add a string or a string view kind of thing, they have to complete this whole laundry list of operations that are just algorithms hanging off of a type. It's ridiculous. But one of the counter arguments to doing something like that was, what about char star? And I said, you just make an overload that takes a char star and it just works. And that's what I've done here. So I think that if we had like the operations that are in boost algorithm, string algorithm, if we wanted to replace those remaining ones, like, split and join and whatever, we would want to have first order support for char stars or any null terminated string. And I think that's important to get right, but I think there's not that many of those operations. And if we added just a few of them, I think we would have a replacement for that. And it's such a rich vocabulary that we're missing from the standard. And the irony is that we've been adding all this stuff to the string, but not the bits that we really care about, like split and join. Like, where are they? So I think there's room for those sitting next to these, and I think they'll be really useful. I didn't explicitly point it out, but these are all in std UC. That may be the name of it. We may not put it in a nested namespace, but that's what I'm proposing right now. Yeah. Any other questions? Yeah.
Rather than global locales, is there any design pattern or language feature we could use to support contexts, like context objects, similar to what's
That's what's done already in format and print, right? You can pass a locale if you want, but otherwise it assumes.
rather than having to explicitly pass the locale everywhere you want to conduct an operation, could we
I see.
to avoid that SG16 motivated insertion into the pipeline to say this is really UTF-8?
So, I mean, the way you do this in other APIs like OpenGL and other graphics APIs do something like this, and they have essentially a context stack. So it's still a global, but you push something onto the stack and you use it locally. And then, because you have to have some way of tying this particular function call to that thing, and there's no way to do that besides passing it or making it a global. As soon as you make it a global and you have the context stack, there goes your thread safety and all the niceties of that. So I think, it's going to be repetitive to put the locale in every place, but that's just going to have to be the way. And the way you make that kind of code work, I think, is you pass the locale as a variable and all this stuff. You put in a function, you pass that in the top, or you set it in some type that is doing all these operations. So you've got the context in the form of a variable that then gets used. And I think that people, if they find the repetitiveness a problem, or if they find that this locale and that locale are not the same and they want them all to match, they're going to do something like that. Put them in a function, put them in a type that uses it, something like that. Steve?
Yeah, just the locale you're talking about is not our current locale.
Exactly. Yeah, I'm talking about some future locale. Right.
The-
Yeah.
the Locale's broken.
Right. The locale that we have right now, everyone considers it a horrible mess. And what we want is a notion of a locale that's a lot more like what they do in ICU. And the locale there is, it's a bag of state that means I know which language we're dealing with. I know which variant of the language we're dealing with. So when you do another operation that I haven't talked about yet, it's an important operation in Unicode, but it's called collation. It's basically less than operations on arbitrary text. And for instance, for German, they have the vanilla German locale, but then they have the phone book locale, which is different from the library ordering. So if you're alphabetizing something for a library, it's different from alphabetizing something for a phone book in a couple of small ways. I don't know what they are, but there's different locales for that, right? And so for the context of doing collation, you want to know which exact flavor of the locale to use. So we need to have a much richer set of information than just everyone's supposed to do all their processing this way and that's set globally. Or even if we were to take the locale and not make it global, but have the same stuff in it has right now, it's insufficient right now. So there has to be some totally new design. And that's what I was referring to. Yeah, thanks for pointing that out. Yeah.
Yeah, so if you're interested in avoiding to repeat the locale or whatever, actually 2 years ago at C++ Now I presented a design for policy propagation through the whole expression tree.
Yeah, so check out that talk if you're interested in seeing that version of things. Any other questions or comments or anything?
Oh,
Yeah.
Question. Right at the start, you mentioned that we could get text from like the network in some chunks, which can split graphemes or something else. Like, is this handled in some way, or do we first need to fetch all the text and process it?
Yeah, so I mean, the way to handle that is usually, I think, to take the stuff you got coming in off the wire and look at the end of it and see if, you expect it to be UTF-8 or 16 probably. You look at the end of it and you say, is this broken at the end? And if it's broken at the end, you find the place where it's broken, and then you take right before it's broken and you process just that part of the text. Right, that's something you can process the whole text from. There might be some peculiarity of the kind of process you're going to do, that you can't just take any old code point. You have to have a range. Like I was talking about normalization, there's a sequence within there where there's like the normalization aware range. Like this stuff can change under normalization, but the stuff before and after it can't. So you might have to do a little bit more work there. And there's not currently an API I'm proposing for that, but you do something like that. You would say, like, if what I'm doing is taking all the stuff off the wire, normalizing it and throwing it in a string, then you'd have to do something like I just described. And if you didn't have the way of determining like where is the chunk where I can like deal with the normalization, then you'd have to like renormalize it. Like you basically have to normalize the whole string and then like pick some spot in the middle and like renormalize the back half of it or something. So you might do duplicate work. So there might need to be that kind of predicate need to be introduced into the library, but something like that, where you're able to tell what I just get bytes, I just get octets off the stream. I need to find where the boundaries are for the important processing characteristics I need for whatever processing I'm going to do on that text, right? And there's an example of that in the 2727 paper, the earliest paper, of like, if I get a bunch of stuff off the stream and I want to transcode it, here's how I find the boundaries where I know like I don't need to combine this with something else because it's a full thing, right? But did you? Okay.
I was just gonna say, I've had some luck basically doing range of ranges and joining them so that the iterator that's being passed to one of these algorithms just hops over the boundary.
Right.
But you have to do some lazy stuff.
So you're saying in that case you would fill a buffer and then put it to the side and not do any memory copying, but put an iterator over the top that could go over all the buffers. Yeah.
It's like throwing them away is necessary or waiting for them to arrive. This is what actually happens underneath the hood in old-fashioned file reads.
Yeah.
But we probably should stick this API in like the network APIs, not
right.
the,
Yeah, but in terms of like, so that's definitely a solution if you're able to just do it. But if you have some steady state thing, that you've only got this much buffer space for stuff for network IO, and you can't take the buffers and do something like Steve was describing, then you do something like I'm describing and figure out when to copy and how much to copy, and then take the sort of suffix that was not copyable because it was a partially formed code point and copy it to the beginning and then fill the buffer from there, that kind of thing.
yeah, it's
right.
also very bounded. So
Yeah.
Like you only need 30 bytes.
Yeah.
For processing.
For the suffix of leftover junk is never going to be more than 3 bytes for UTF-8, for instance. Yeah. Or 2 bytes for UTF-16. Yeah. Okay. Anything else? All right. That's it. Thanks, everybody.